is that if I'm the client and there is some method, I can use the method without, I don't know how I want to draw this, but I can use the method without knowing what the actual body of it is, right? So if you're given just the contract for a method, you could use the parameter modes based on the variables that you have to input. You could use what the description of the contract says. You could use the requires and the ensures clause in order to basically figure out what the method is going to do. You could do that without seeing a single line of the code. And it's up to the implementer to actually provide the code. It's a way of separating out concerns so that the client doesn't have to worry about how the code was implemented. You do this all the time when you call things like out.println or stack.push. You don't know exactly how it works, but you're just kind of assuming that the implementer has done their job correctly and that you can use the method accordingly. Today and Thursday, we're going to be extrapolating this idea to while loops. So instead of a method, it's going to be a while loop. And instead of a contract, it is called, do you want to take a guess, a loop invariant. A loop invariant is a way of thinking about while loops so that you, as the client, can look at a while loop and without even seeing or knowing what the code of that while loop does, you could probably infer what the loop does, what updates are made to the variables, and what the final state of some of the variables are. And again, this just goes back to the separation of concerns between the client and the implementer. I didn't draw the implementer up there, but whoever wrote the while loop will know what the code looks like. But the overarching thing here is if you are given a while loop and a loop invariant, so just the condition of the while loop and then the loop invariant, you should be able to tell me what the while loop does while knowing what none of the code actually is. And we'll talk about how we do that. But that's the theme for today and Thursday. Okay, so when a method call is what a method call does is described by its contract. The precondition is a property that is true before the call is made, and a postcondition is a property that is true after the call returns. We have something similar in the loop invariant, just called the loop invariant, which I'll talk about. I think it's on the next slide. Yeah. What a while loop is described by this term loop invariant, which is a property that is true every time the code reaches a certain point. In the case of a loop invariant, the loop condition test. So I'm going to skip ahead so that I can draw this, but this is the flowchart version of a while loop where you have, you're coming into the chain of command here. You have the test, and then you have, if it's false, it goes and it does something else. After the code is run. But if it's true, you do some body of code. You loop through an array or do something, but then you come back around and you do the test again. The loop invariant is something that is going to be true at these steps right here. So before you enter the testing side of a loop or the testing part of a loop, which could be like while, like I is less than length of the array, other examples, is something, the loop invariant is something that will be true every single time that you reach that point in the code. Okay, so we'll go back. Okay, and that's what's called a loop invariant. Why is a loop treated differently than a method call? Simply put, experience shows that this is a good way to think about loops and think about what loops do so that you don't have to potentially dig into thousands of lines of code that are contained within a while loop and trace every single function call, trace every single variable that's updated. You can just look at the loop invariant and to know what happens. Is this just for while loops? Yes, but the same idea could be applied to for loops. Some modifications are required. We never get into that. Don't worry about that. But for loops are basically just while loops, but packaged. So like if you've ever noticed, for loops have like, or while loops have like int I equals 0, and then you have your while I is less than something, and then in the loop you do like I plus plus. For loops just do that, but then they package it into something that's actually nice to look at. So you could extrapolate this out to a for loop, but we will not in this class. You can do it on your own if you want. It's a fun exercise. Maybe that's what you guys can do this summer if you're not doing anything else. Okay, since a loop invariant is true every single time it goes through the loop, it focuses on what does not change rather than what the loop does. It focuses on what the loop does not do. And through this, you can tell some things about the code that are important. So it might say that this data structure is not updated, or some other property is not updated. And the example they give in the slides is pretty good, so it'll make sense once we go through the example. Okay, here's an example of a while loop. While test is some condition, and then you have a loop body, which does something. The loop invariant is a property that is true both here, just before the loop begins. So this is an important step. It's not just after the loop body has executed once or twice or three times, but it's also before the loop body has executed at all. And here, just after every execution of the loop body. Okay, here's the example. The example that we're going to give is the append method, which takes in a queue and appends it onto another queue. So if you have a queue of, say, 1, 2, 3, and then you have a queue of, say, 4, 5, 6, afterwards, this will be 1, 2, 3, 4, 5, 6. And the other one will be 0. So let me actually write that out so that we can keep track of it. But we have this as a queue of 1, 2, 3. And then we have, what are we taking in? It's called a queue. Queue as a queue of 4, 5, 6. This is our before state. So before the function runs, and then we have our after state, where this will be 1, 2, 3, 4, 5, 6, and Q will be the empty set. And that's what happens after. So it hands the queue onto the other queue. In terms of contract language, the insurance clause here is that the new value of this is equal to the old value of this concatenated. Remember string theory, that sign multiplies sign, it's a concatenation sign with the old value of Q. It updates this, clears Q. Those are the parameter modes. This is just a very nice contract. Okay, and then here's an example of a method body of how you would do this, or an example of what you might do. The generic type X is equal to Q.DQ, and then you do this dot on Q. Very simple way. But as you can see, it's in a while loop, so we can have a loop invariant about this. So what are some things that are true every time that we test the loop condition? So based on what we know about just the before condition here, considering just the state of things before the while loop executes, as well as the loop condition, what are some things that we know are going to be true every single time we get to the test condition, and every single time that we go back to the test condition? What are some things that are going to be true every single time? Yeah. Yep, exactly. So always, 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 the loop condition is going to be something that is going to be true. Every single time true. Because if it isn't, then we break out of the while loop, and we don't actually need the loop invariant right now. That's be true after the while loop. Okay, what's something else that is going to be true? This one's a little bit more difficult, I will say. And it has to do with the combination of the two Qs. Yeah. This will have a value to yeah. So like this will T of X will be something that we can onQ. Something we can onQ. Every single time we should have something to onQ, because Q will have a length greater than 0 or greater than 0. To get this final one, let's go through what everything looks like during each iteration of the loop. So first we have 1, 2, 3, and I'll draw them like this: 4, 5, 6. That's before the loop starts. Afterwards, the first loop, we have 1, 2, 3, 4, and 5, 6. We have 1, 2, 3, 4, 5, and then 6. Okay. what can we say is always true at the loop condition based on looking at what Q and this look like after each iteration? This is Q. These are separate Qs. But what do you notice about these things?
There's always a substring or the original of this. It's always part of
Sure. Yeah. Whole value of this is a substring of the new value of this concatenated with the new value of Q. On that same line, what do you notice about the elements? Yeah, Q is the suffix of this. Q, the new value of Q is the suffix of the new value of this. Okay, there's one final thing that combines those two things together, really. Look at the elements. What's changing? I'll draw the last one too. But more specifically, look at each iteration. Just look at this concatenated with X, or this concatenated with Q. What do you notice about this concatenated with Q? So this concatenated with Q after the first time is 1, 2, 3, 4, 5, 6. This concatenated with Q the second time is 1, 2, 3, 4, 5, 6. This concatenated with Q the third time is 1, 2, 3, 4, 5, 6. This concatenated with Q the fourth time is 1, 2, 3, 4, 5, 6. After the loop ends, the concatenated with Q is 1, 2, 3, 4, 5, 6. Okay, I said it 5 times. What is the same? Yes, this concatenated with Q is always going to be the same thing. And inherently, another thing that we could say is true is that the cardinality of this plus the cardinality of Q is always equal to the cardinality of them concatenated. Meaning we don't lose any values. That's something that's true every single time that the loop condition evaluates. Or that's a bunch of things that are true every single time the loop condition evaluates. And if we go through the tracing table, you can see this. First condition, Q.length is greater than 0. A bunch of other things. You DQ and then append. You continue doing it. What is true the first and second time? The value of X is not involved in the loop invariant because there is no X when we first hit the loop. So a lot of times people will try to include things inside of the loop. I don't have the loop written up here. A lot of times people will try to include things that are defined inside of the loop as part of the loop invariant. But you have to remember that because it needs to be true before the while loop begins executing, things such as X or T, X is the name of the variable, cannot be included in the loop invariant because they don't exist before the while loop. Okay, and then afterwards, finally, we go through the entire thing. And afterwards, this is 1, 2, 3, 4, 5, 6. Q is empty. Okay, whatever is true the last time we test the loop condition is also true here after the loop finally terminates. So after the loop terminates, you'll see that a lot of the things that we said were true each time the loop condition evaluated are also true after the loop ends execution. Some things aren't, like Q.length is not greater than 0 anymore because it is equal to 0. X is not something that we can on-Q because X is not within the scope of the loop anymore. But I think all of these are good as well. Like the old value of this is still a substring of this concatenated with Q. And the important one, this concatenated with Q is the same every single time you hit that loop condition. Okay, some things do not change. The lengths of the strings are non-negative, does not change. So the cardinality of this is always going to be greater than or equal to 0. And the cardinality of Q is always going to be greater than or equal to 0 because you can't DQ from an empty string. So that's kind of pedantic. This goes without saying. It is no more useful than saying 17 is less than 42 does not change because it's kind of a mathematical fact. So things that are always going to be true, regardless of anything, are not good candidates to be loop invariants. So a good candidate for a loop invariant would not be something like Q is a Q. That doesn't change every single time the loop enters the loop condition. So if you're given a while loop and you're asked to come up with a loop invariant, don't choose something that's like obvious. Don't say this class is CSE 2221. That's true every single time the loop executes. It has to be something that is at least interesting. The sum of the lengths do not change. This is true, but we can say more, which is that in addition to the lengths always being the same, this concatenated with Q does not change. This is essentially the same thing as saying the cardinalities do not change, although it is stronger because we're saying not only do the cardinalities of the sum of this and Q not change, all of the elements remain the same as well. You could have a loop that changes the values, but the cardinalities stay the same. But we're doing something stronger here, which is saying that none of the values are lost and everything is maintained. If this concatenated with Q does not change, then the cardinality of this plus the cardinality of Q also does not change, but not vice versa. So you can have like a bunch of Qs with a bunch of different values where you're concatenating things that are different than the original concatenation, in which case the cardinality or the vice versa would not be true. Okay, so how do we express an invariant? How do we say that the concatenation of strings does not change? We need to talk about both of the current values, which if you remember contract notation, we do by just not including a hashtag in front of it, as well as the original values of the variables. So if you were reading this out like an English person or like a person speaking English, you would read out that this concatenated with Q, or the values of this concatenated with Q, are always equal to the old values of this concatenated with the old values of Q. And if you look at the example that we have up here, that is exactly correct. 1, 2, 3, 4, 5, 6, 1, 2, 3, and 4, 5, 6 is equal to 1, 2, 3, 4, 5, 6. It always remains the same. Now, it only needs to be true. Side note, I don't know if this is in the lectures, but at the testing condition. So if I like take X and I like mess around with it a bunch, but then I restore it back to the original value before I on-queue it back to this, it doesn't matter that I've changed the values or that I've messed with things throughout the while loop. The only thing that matters is that when we get to the testing condition, the loop invariant that I've defined is maintained. Okay, so here is an example of a loop invariant that you might write for this while loop. It's basically just 3 lines. You're telling people that this and Q are updated. You're saying, oh, it's actually 2 lines basically. You're saying that this and Q are updated, meaning that you're removing values from Q and adding them to this. And then you're maintaining, which is what the keyword is for a loop invariant, the fact that this concatenated with Q, or the values of this concatenated with Q, are equal to the old values of this concatenated with the old values of Q. And that's your loop invariant, or at least part of it. And then you have the while loop. Yeah. The first time. And I guess it could be both. So actually, in this case, I would say it would be the values of this and the values of Q here. But it also should not matter because since it needs to be true here, it needs to be true here. The property is going to be maintained both at the beginning of the while loop as well as each time that you get to the testing condition again. Okay, but I think this is not the end. Oh yeah, this is just going through. Java tag introduces the list of variables whose values might change in some iteration. Any variable in scope that is not listed as an updates mode is by default, remember, a restores mode parameter, meaning that the loop body does not change its value. However, in this case, since we're on queuing and dequeuing from both of these data structures, they are updates as opposed to restores. And this is the Java comment that says that the loop invariant will be maintained over time. Okay, so we have our final loop invariant here. If you have a strong enough loop invariant, you can trace over a loop in a single step and predict the values of the variables when it terminates without tracing through the loop body even once. So if we just had, like if we just had this as well as the method header, what we'd be able to deduce based on the loop invariant as well as the while condition is that this would be getting all of the values. So since we know that it's going to update this and it's going to update Q, or it may update this and it may update Q, and we're going to be looping until Q dot length is equal to 0, because that's the value of Q dot length. That's what the while condition says. It's that Q dot length is going to go until it's equal to 0. Those values have to go somewhere because of the loop invariant, because we said that the value will be maintained. So the only possible thing that this loop could do is append all of the values of Q onto the data structure this. So it's kind of cheating because we already know what the loop is going to do. But if we didn't, we'd be able to deduce it. And that's the idea of a loop invariant. However, there's one final piece of the puzzle that we need, which is that we need to show that it's going to do something, essentially. We need to know that the loop is going to terminate at some point, because what's to say that Q dot length will just never be equal to 0? And in that case, we would just have an infinite loop. So the loop invariant needs to show that progress is being made towards the while loop condition being false. Pretend you cannot see the loop body. Can you still trace over this loop? When execution reaches this point, we know two things. We know that Q dot length is going to be equal to 0, and we know that this concatenated with Q is going to equal the old values of this concatenated with the old values of Q. So since we know that Q has to be 0, or the length of Q has to be 0, it can't have any elements. So where do those elements have to go? Well, they have to go onto the end of this. Right. So we know the loop invariant is true, and we know that the length or the cardinality of Q is less than or equal to 0. So combining those two, the only possible values or the only possible state that this can be in is 1, 2, 3, 4, 5, 6, with Q being an empty string. Does that make sense? Do we know why that must be the case? Okay, then yeah, that's loop invariance. Okay. The loop invariant is true just after the loop terminates if the code that tests the loop condition does not change the value of any variable appearing in the loop invariant. So what this means is as long as this test condition does not modify anything contained within the loop invariant, so this or Q, then we have a third case or a third place in which the loop invariant will hold, which is after the loop has ended. What do we do in the case that the while condition does change the variables listed in the loop invariant? Well, we just don't include changing any variables in the loop invariant. So the biggest way that this manifests is a lot of people, for whatever reason, like to do like while plus I is less than like array.length. This is an example of you changing things within the loop condition, which is very bad practice. So just never do that. As long as you do not modify anything within the loop condition, you can also be sure that the loop invariant is going to be true after the testing condition has run its course. So best practice is just never update variables within the while condition. This should only be for testing booleans. You should never modify anything by, say, increasing the length of I, or doing something like while I is less than Q dot append 4 dot length. This would be bad. This would be very bad. Don't do that. But as long as you don't do that, as long as you just have normal while loops or while conditions, you can be sure that your loop invariant is going to be true in 3 places: before, during every iteration, and after the while loop has concluded. Okay, if the loop invariant is true at the 2 red points and test updates nothing, then the loop invariant is true at the 2 green points. Okay, then yeah, also it can be true at a 4th point, which is directly after the test. So if you have a loop invariant which is not modified within the testing condition, the only place that that loop invariant could be different is here during the loop body. So let's say that for whatever reason our DQ method just cleared everything in Q and then added it back for some reason. And added like a temporary Q. The loop invariant wouldn't be true for that brief moment of time that all of the values in Q were in that temporary set. But as long as you added them back to Q before you hit the testing condition, the loop invariant would hold. So 4 points at which the loop invariant can be true. It's always going to be true no matter what at the 2 red points, as long as you have a strong loop invariant. And then if you do not update anything within the testing condition, which you should not be doing, then it will also be true at these 2 other points. Okay. Best practice, code that tests the loop condition should not update any variables appearing in the loop invariant. An easy way to achieve this is that the test should not update any variables at all, because it's just bad practice. Okay, the loop does not terminate until and unless the loop condition is false. However, a loop might never terminate, so you need to show that it does. So if you remember going back to the loop invariant that we had, we need to make sure that q.length is eventually going to be equal to 0, because right now we're banking on the fact that q.length is decreasing throughout the while loop code, but it could not be. We could be moving elements from this to q instead of vice versa, and everything would still remain the same. So if we simply reverse the body of the loop where we did this.dq and then q.onq, the loop invariant would still hold. This concatenated with q would still be equal to the old values of this concatenated with the old values of q. It would still be updating this and it would still be updating q. But we would never break out of the loop because q.length would never be equal to 0. So that's the last thing we need in our loop invariant. Is a progress metric or a termination function or a variant function. It's just an integer valued function of the variables in the scope, which always decreases when the loop body is executed once. So the easiest way to do this is to just say that the cardinality of Q decreases over time. And what this means is that eventually, at some point, even if Q is full of 8 billion elements, as long as we're decreasing the cardinality of it over time, eventually q.length will be equal to 0. And that's a loop invariant. Updates this, updates q, maintains that the values are the same, and over time decreases the cardinality of q so that eventually the while loop condition will be equal to 0. Biggest way that this manifests is basically given the loop invariant and then given the while loop condition, could you tell what happens to the variables after the loop has run its course? Same way that if you were given a method contract and then you were given the method header with the precondition and the postconditions, you should be able to tell me what the method can do based on just the contract, if the contract's written well, which usually it is. And then the Javadoc annotation claims that the loop decreases the stated progress metric. And the progress metric here is that the cardinality of Q will be decreased. So in conclusion, even if you do not choose to write down a loop invariant or a progress metric, if you think about loops in these terms, it can help you avoid errors and bad practices in loop code. If you would like to, you can spend the rest of your days writing loop invariants for all of your while loops, but you do not have to. You probably shouldn't because it would be pedantic. But it's a good way to think about while loops and think about how things are changing within the while loops to prevent you from having things like off by 1 errors, wrong or missing code, and then declarations of variables outside the loop that are only used inside the loop body. And that's loop invariants, or at least part 1. We have the sequel on Thursday. But that's all that there is today. So yeah, gift of time. Do you guys have any questions? I got the sample final, or not the sample final, I got the actual final from Bucci last night. So I just need to double check to make sure that I didn't accidentally write any of the same questions as him on my sample final that will be released probably tonight. So you will have a week to work through the sample final, ask me any questions. If you want my advice, I would treat it as if it's a real final. So writing the code without looking anything up, without using an IDE, find yourself, see if you can finish it in an hour and 45, and then grade yourself because I'll be releasing a key as well. All right. Free to go.